A very good morning, good afternoon, good evening to all my dear friends, participants and students for this NPTEL MOOC course, the title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you all know, there are three broad topics for this course: forecasting, first one; regression, the second part; time series, the third part. We are in the second part, which is the area of regression and discussion. This is week number 8 and we are in lecture number 39. Now, if you remember, in the last class we started discussing very briefly, though considering the time we ended, about different type idea of why the squared error loss may not be the exact one in trying to estimate, because due to asymmetricity in the estimation. And I did mention the name of the loss function which portrays that is known as the LINEX loss function. And if you remember, I mentioned is linear exponential, that is, there are two parts, one is the linear part, one is the exponential part. We will discuss about here continuing the LINEX loss function, what is the expected value of loss, what we mean by that, and what is the risk of estimation from the point of view of statistics and in the concept of regression, and that will give you a lot of idea of how different type of loss functions can be utilized. Now, before I discuss this slide, I will discuss about the asymmetric loss function, which is LINEX loss. And I did mention it has two parts, linear and exponential, and they will play an important role, which we will discuss within few minutes. Now, if you have theta, this theta has nothing to do with the theta what we discussed in multiple linear regression. Theta is just a parameter which you want to estimate, just a value you want to estimate. If theta is the parameter and theta hat is its corresponding estimate based on the statistical methods, then obviously there is an error. If you find out theta hat to be exactly equal to theta, that is no error in estimation. If there is a difference, there is an error, and that error is denoted by delta, which I will mark with a certain color, considering is yellow, orange. So, this is theta is equal to, the delta is equal to the difference between theta and theta hat. So, theta hat can be either greater than theta or less than theta, hence delta can be positive or negative. Now, if you consider this is the error, because if you remember in the concept of regression models, what you had was, you had, I will use a different color, your actual value was yi corresponding to the ith reading, and the estimated value was y hat I. So, the difference was given by the error, which is E, not epsilon, E I for the ith reading, and square of that, summation of that, actually which is summation of the error square, gave you the idea of ordinary least square. That is why it is given. For example, in the ordinary least square or squared error loss, it will be denoted by theta minus theta hat square, or you can use the concept of weights also. So, if theta minus theta hat is positive, then you give a higher weight. If theta minus theta hat is negative, you give a lower weight. So, it can be given at, say for example, the weights for theta minus theta hat is positive, you give a weight of 2, and theta minus theta hat is negative, you give a value of 1.5. In that case, it will be given as 2 into theta minus theta hat square if theta is minus theta hat is positive, and if theta minus theta hat is negative, will be given a weightage of 1.5. Now, in order to overcome this concept of equal concept of loss for both positive and negative, we come into the realm of LINEX loss function, which is linear exponential loss function, and that, as I mentioned, consists of linear part and the exponential part, and I will highlight that. The linear part is given by this, which is the difference with the negative sign, which is different. A is the shape parameter. As you know that in any distribution in statistics, there are three parameters: shape, scale, location. So, A is basically the shape parameter, and the term linearity is A into theta minus theta hat or A into delta. there is a -1 sign also here, and the exponential part which I will highlight with a different color is given by e to the power a into delta. So, that is to the power, and this whole thing is multiplied by b. B is a scale parameter. So, you can have b as 1, 2, 3, 4, but its consequence in trying to portray what is the characteristics of this LINEX loss function, b can be considered as 1, even if it is b is 2, the overall implication that it will be only scaled up, the concept which I am going to discuss. So, actually again I am repeating, the LINEX loss, which is loss function for delta or loss function of theta and theta hat, which are the, one is the parameter, one is the estimate, it is given by b, the scale parameter in the bracket multiplied by e to the power a delta minus 1, and the loss function looks like this, and here I will spend some time. Consider b is 1. So, your loss function I will use a different color for each case. So, this implications will be important and easily discernible by you. If a is positive, so you will have a and also delta is positive. So, you will have a positive, delta positive, here is minus a delta minus 1. So, the exponential part for delta positive and a positive is much more than the linear part. But interestingly, if a is positive, continues to be positive, and delta is negative, in that case the exponential part with the minus sign becomes 1 by e to the power a delta. Hence, in that case, when again I am repeating, a positive, delta is now negative, then the exponential part is dominated by the linear part. So, the linear part is in a sense dominated. So, if I plot that diagram, I will again use the violet color. This is the loss function, this is the delta part, this value is 0 delta. So, I will mark delta along this axis. So, in the first quadrant it is positive, in the second quadrant delta is negative. This is the loss function L delta. So, in the case when a is positive, for a being positive I will use a different color. So, a is positive. So, in that case the exponential part dominates for delta positive. So, you will actually have the LINEX loss looking like this. So, it increases more in the first quadrant, and in the negative quadrant, in the second quadrant it is not increasing to that extent. So, this is the graph. And if a is negative, I will use a different color, a is negative, and I plot it in the same diagram with a different color, because in that case delta being positive, a being negative means in the first quadrant the linear part will dominate the exponential part, it is just the reverse. For a positive, again I am repeating, a positive, delta positive, exponential part dominated in the, and it was dominating in the first quadrant. A positive, delta negative, the linear part dominated the exponential part in the second quadrant, and a positive means the red color A. With a negative, which is green part, the characteristics are just reversed. That means, in the first quadrant the linear part will dominate, in the second quadrant the exponential part will dominate. So, if you have that, there the graph I will use a different color, consider I will use, let me use the color, I will use the light blue. So, in this case is this. So, the concept of the green and the blue go together, light blue go together, the concept of red and violet go together, in the sense for positive A and negative A. And you can easily plot it to see, very simple, just plot some values in the Excel sheet, you will find it out. And this is what I have done. If I take the positive negative values I have plotted, and A values can be taken corresponding to the value that you have A as can be taken as minus 1.25, minus 1, minus 0.75, minus 0.5, plus 0.5, plus 0.75, plus 1, plus 1.25. And I have marked the values of delta along the x axis, marked the values of loss function along the y axis. And the graphs I have all plotted. If you look carefully, the graphs coloring scheme would give you that idea. So, for the case when you have this light blue one, actually which means in the case of the light blue one, you will have the case of, say for example, 0.5, and in the case when you have the brown one, it would be in the case when you have this mode may not be very visible here. I will try to rectify that in this slide and make it much clear, but whatever I made a point in the discussion would be more than sufficient to highlight. So, if required, I will spend few minutes here also. So, I will now discard and go back to the Excel sheet, and this Excel sheet I will just save it in the format, which if you remember, the Excel sheet, even though if you see here in the actual Excel sheet, there is one sheet Excel file, sorry, one sheet is distribution, one sheet is forecasting, one sheet is regression, and one sheet in time series. But when the Excel files are shared, they will be shared with you separately. So, one for forecasting, one for regression, one for time series. So, this part which is related to regression, the exponential part, I will mark it here and just show it to you. Now, I will do it in the distribution part, so it will be easier. So, when it is shared, you will be aware of that. I will spend some minute here. Let me check all the distributions are there. Yes. So, I will mark as first is the value of A is equal to, I will put the value of A, say for example, it is plus 1.0 for the time being, I will change it accordingly. This is the delta value, this is the loss of based on delta. Delta is the difference between theta and theta hat. So, I will basically do it here. So, if I will have the delta value starting, say for example, difference being minus 3, and I will increment it with values of 0.1. So, I have minus 3 the delta value and it goes up to 2.2. So, I will mark it to 3. So, these are the delta values. Now, if I need to find out the loss is, if you remember, B I am considering as, let me consider B also in case if you are interested, just to mark it. So, I will take B as 1 initially and keep changing it. So, the loss is B, and in the bracket you have exponential of A multiplied by delta minus A multiplied by delta minus 1, and the bracket, let me check whether I have taken it right, closes. I think there is an error, let me double check it, whether the brackets are correct. So, exponential done. So, for now I need to fix the value of B. R1 is fixed because it is not changing. Changing means for all the calculation, I will keep changing it one by one. E to the power A is also not changing. Delta will keep changing. Again, next term is minus A into delta, that is also fixed. So, I copy it. There seems to be some problem. Let me check if A can be made value. E to the power. Okay, I think I should have put a bracket here. My mistake. And this value is fine. Yes. So, the first term, which is e to the power this, let me check, it is in the same bracket. Yes. Now, I think it should work. Yes. Now, the equation is perfect. So, you have the equations given here. So, let me check. Once you have this Excel sheet, please check the equation, but I am sure it is correct. So, if I plot it for a value of A is equal to 1 plus 1, B is equal to plus 1. Let me check, see how the graph looks like. So, this is the loss function. If you remember, I mentioned that for positive values of A and positive values of delta, it is exponential part is dominating the linear part. So, let me take this graph above and change A to negative values. So, it will immediately give me the idea and to all that the discussion is making sense practically also. So, let me make A as -1 and check the graph. See, it changes, flips. If I make B as +2 or 0.5, it will be scaled up. If I make it is 0.5, it will be scaled down. So, you just notice the values in the y axis. If I make it A value is 0.25 with a value. So, here it is slowly becoming, the concept of A is small. So, the dominance of exponential part and linear part are not that much when A is very high. So, if I am able to draw the diagram, I will remove it, and what I will do is I will take delta values and I will take different B, let it be 1. So, B values I will take 4 such combination as B as 1, and this I will take as -1.0, then -1.0, then -0.5, then +0.5 and +1.0, and mark all these values. So, this is the loss function for A is equal to -1.0. Similarly, I have the next plot which I will do is for A 0.5, the next one is for A is 0.5 plus, and the next one is for A plus 1.0. So, I have these values, I will mark it. So, if I take this, if I copy, and obviously the change would happen here. The B value changes, so it becomes S, and the A value changes, it becomes S2, see, it's shifting. Then if I make it as for this becomes T, this becomes T, because I am taking values of A as -1, -0.5, +0.5, +1, and this becomes T. Finally, if I copy it, the value becomes U, the cell value, value means cell value, this becomes U, this also become, no, this becomes U, done. Now, this is a huge value. So, let me check. So, if I copy it here, because 10 to the power 12 is a huge value. So, if I plot it, let me check whether all the values can be plotted, because some values are 10 to the power 12, some values are only 10 to the power 1. So, that this is a huge. Yes, this would make some sense. Yes, this graph which you see is an interesting one. So, you have a is equal to minus 0.1, if you see it clearly, the orange one, let me make it red for clarity for all of us. Let me make the gray one as, say for example, green, and the yellow one let it be, because these three colors are easily distinguishable. So, if you see the graph, so here you have for a minus 1, you have the red line, red graph. For green one is for a minus 0.5 and a plus 0.5, it is the orange one. Now, you see the difference, that overestimation and underestimation. It is so stark and so simple to understand using this graph. So, once you have that, this is basically the graph of the loss. LINEX loss function. Versus delta for different values of a. So, I will save it. So, that means when it is shared with you all, you will have that information available. And these lines are the losses. I will also check them. So, say they are from the values of, they start from which value? From 0 to almost 30. So, it will be better if I format that. This is from till 30. This is done, and that axis I also increase the font size for greater visibility for the losses. Similarly, I increase the font size for the x axis, which is delta, and delta, if this is delta actually, but if you see here, this is giving you the reading number. So, do not be confused about that. I will make it 15, and these values are given as the legend. It will also increase in size. So, that will make sense. So, this is the LINEX loss function for delta for different values of a. And a values, as you can see, minus 1, I will make it black bold. So, minus 0.1, minus 0.05, plus 0.5, you have this graph. So, I will save it later, but with this discussion, I will go back to solving or discussing the LINEX loss problem and the concept of that. I will save it with a particular size, so anybody can utilize it once the data set is shared with you. I will save it first. Now, I go back to the Excel sheet. So, where we were. So, this is the PPT file. This we were discussing. Based on that, we went back to the Excel sheet. Now, why this LINEX loss or asymmetric loss very interesting? If you expand it for very small values of delta. So, if I expand it using the small values of delta, I use the expansion of the exponential series, and it becomes 1 plus a delta by 1 factorial plus a delta whole square into factorial 2 and goes on till infinity. Now, if I consider a delta is very small, delta is very small, then square cubic terms all can be neglected. In that, not square, I won't neglect the square, sorry for that. Cubic term and higher terms can be neglected. So, if I have this should be 3 of order 3. So, cubic terms higher can be neglected, which means 1 cancels, a delta cancels, the only component is the squared error, which means that for very small values of delta, the LINEX loss can be approximate to the square error. And this also you have seen in the Excel sheet. Let me go back again to the Excel file. If you zoom in at the values or when delta is very small here in this region. So, if you zoom in and around the value of delta 0, it looks almost like a squared error loss for very small delta. That means both positive error and negative error are being equally penalized. That means for small delta, you can utilize that LINEX loss as an approximation for the squared error loss function. Now, before I come back to this slide I am just showing, but I will talk more. Now, where this LINEX loss are used? So, I will consider 3 different examples, and they are not in the area of finance, not in the area, there are a variety of problems. First, consider a dam is being built. So, for any dam you have a particular height. So, what does the height mean? Height means it is able to withstand the pressure of water. Consider for building up a dam, you have 2 cases. Case 1, where the dam height is built more than it is required, and in the other case the dam height is built less than as is required. Consider the actual height should be 120 feet. In one case it is 122, case 1, in another case is 118 feet, case 2. If it is a squared error loss, the errors in both the cases are equal. Why? 122 minus 120 plus 2 whole square 4. Case 2, 118 minus 120 minus 2 whole square is plus 4. So, both for overestimation and underestimation, if you use the squared error loss, because you are squaring them, that concept of overestimation and underestimation would not make much of a difference. But practical thing, flood comes, probability of the flood breaching the dam is much higher in case 2 when the height is 118. But in the case of when it is 122, the probability of the flood breaching the dam is less. Even though the cost of building the dam for 122 feet in case 1 is higher than 118 in case 2, but the catastrophic natural disaster loss in case 2 is much higher, which means underestimation is a problem, which means you need to take A as negative. If you remember underestimation being problem, it will increase for delta negative, it will increase very sharply for A negative. Consider another example where overestimation is an issue. Electrical panel, there are very sophisticated fuse, people are working life, average life of these machines is considered 6 months, and because based on that you need to change the high end fuse circuit, trip switch, for which the electricity flow will be stopped if there is a fluctuation. So, all these electrical very sophisticated fuses have a life, and that what I said as 6 months. Consider case 1 estimation, or rather than 6 months, it is planned that change will happen at 8 months, and in case 2 change will happen at 4 months. In ordinary least square error, the difference is case 1, 8 minus 6 is plus 2 whole square is 4. In case 2, the difference is 4 minus 6 is minus 2 whole square is 4. So, in both the overestimation and underestimation, for the case of squared error, there is no consequence. Practically, it is a problem. Why? In case if you change those switches, very sophisticated fuses, at the end of 8th month, then the probability of a catastrophic loss is much higher, because the voltage fluctuation will affect where actual life is 6 months. But if we change it in the 4th month, then the probability of that affecting is much lower. Even though work stoppage and all these things are there, but the catastrophic loss in the case when it is 4 months is low, which means overestimation is a problem. So, in the example 1, civil engineering, underestimation of problem, replace with A negative. In case 2, electrical case, overestimation is a problem, replace A with positive, and there can be different of examples in order to make such things very plausible and very practical. Now, when you are trying to utilize these ideas of LINEX loss function, you also try to bring that into the regression models. And why? Because in many of the regression cases, the idea of overestimation and underestimation can be a problem, and which has to be taken care in a very nice way. Now, I will only give the results, and based on the results we will consider. Now, if you remember, we were discussing about theta, and theta was basically a parameter which was found by multiplying this. Theta hat was L transpose into beta hat which have been found out from the estimation problem for the linear regression. In the ordinary least square, this is the best estimate, because L is a constant, beta hat best estimate is beta, hence the best estimate for theta is also given, theta hat is also given as, say for example, theta. So, L would not have any consequence because it is a constant. Now, in case if you want to utilize the concept of LINEX loss, it can be found. I am not going to go into the theoretical details. The actual theta hat under the LINEX loss is given by this, and this term everything is known. Sigma square is the error from variance from the error. A is the parameter for the LINEX loss, whether positive or negative. L we know, assumed, and this part which I will mark with a different color, this we already know. We are being utilizing it so many times, which is x transpose x, that whole thing inverse, and then multiplied by L. So, based on the fact whether A is positive or A is negative, your theta LINEX can be overestimated or underestimated. Based on that, you can compare this theta LINEX. Theta LINEX means theta hat LINEX found out from the using the LINEX loss function, and you can compare that with corresponding to theta being found from the squared error loss function. Now, the question is that practically how does it would make sense, and I will come to that within few minutes. Now, before I discuss, I will just state the idea in details. So, consider L is all 1. So, if you have that beta hat, the same problem which we are considering in the case of the problem for the estimation of the return for the Tata Motors returns based on NSE returns, India and Indian rupee to US dollars in rupees, and the Brent crude price in euros. And here also you have a beta hat which is estimate. Based on that, theta hat is given as 1.04560. You can just multiply this row vector into L. L values are all 1. Now, if I consider sigma square as 0.0052, which you can estimate, then based on A values -1, -0.75, 0, +0.75 plus 1, the theta value had values for the case when it is square error, it is fixed, because it does not depend on the next, the value comes out to be this. When I keep changing the values for the LINEX loss based on the value of A, you have the different values and the differences are given. And here I want to basically highlight, for a value of A positive, LINEX loss overestimates. For a value which I am marking in, say for example, green. So, this overestimation decreases, and very interestingly, when A is 0, obviously that part for the LINEX is not there, both the values for A 0 are same as it should be, because the second term which you had A sigma square by 2 and L transpose in the bracket inverse of x transpose x into L, that total part will vanish because A is 0. Hence, the value of theta hat LINEX and theta hat squared error both are 1 plus 1.0456. Hence, the difference is 0. But when A becomes positive, you see in that case the part of estimating theta hat using the LINEX loss, this value is low. Interesting part, overestimation and underestimation difference for the case of A minus 1 and A plus 1, the differences are same, of the same quantum, but with a different sign. What is that? For A minus 1, it is minus 0.7801, and for a value of A plus 1, it is plus 0.7801. If I consider the value of, say for example, A minus 0.75, A plus 0.75, the differences comes out to be this, which I am putting a violet tick mark. Quantum is same 0.5851, but one with a minus and one with a plus. Now, before I proceed, I will try to talk about from the practical sense. Practical sense, you may be thinking, why am I discussing this? Consider this. If somebody wants, the idea is basically you cannot compare apples with oranges, which means that depending on the environment you are working, you have to choose that estimate accordingly, which is, say for example, somebody is suffering from fever. So, best to give him or her a medicine in fever rather than give him or her a medicine from stomach upset. Or somebody is suffering from stomach upset, it's best to give that medicine and not give the medicine for fever. Obviously, because if antibiotic is given, it will definitely bring down the level of fever or relieve the pain of stomach upset, but utilizing the right medicine for the right disease is in the same way trying to utilize the right estimate under the right environment. So, in the case, if you remember the example I given, for the dam building problem, if underestimation is a problem, you will use A as negative and solve that problem, not concentrate on A positive, because that would not give you a practical answer to be solved in the practical sense. You can get very nice theoretical answers, practically it would not make sense. Similarly, when you are considering the electrical example, try solving it considering the example where A is positive, where overestimation is a problem. Because utilizing A as negative, you can solve it theoretically, fantastic, but it would not make any sense to you in order to solve the problem. Now, having said that, I would like to discuss further on that how the ideas of theta can make sense accordingly. So, before I move to the other graphs, slides, I will discuss here why I discuss this slide. Now, if you remember that L value is given for beta naught as 1, beta 1 hat values, beta naught hat corresponding value of L place is 1, beta 1 hat the corresponding value of L is 1, similarly for beta 2, similarly for beta 3. Now, where we make a change? Consider that rather than taking, you have all the beta values, rather than taking 1, 1, 1, 1, if I take as 1, 0, 0, 0, in that case I can find out the value of theta as beta hat and solve the problem very simply, and utilize the concept of LINEX loss, utilize the concept of squared error in order to compare the values as it is given in the slide, and we will come to that. Similarly, when I considered the L value as 0, 1, 0, 0, which means I am putting all my stress on trying to find out beta 1, beta naught's effect, beta 2's effect and beta 3's effect all are 0 because the corresponding values in the L vector, whether column or row, whichever way you mentioned, are all zeros. So, based on that you can solve the problem and continue doing it accordingly. And with this I will close the class and continue more discussions where I take different values of L and try to solve the problems accordingly. Thank you very much and have a nice day.